Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Look at this white thread. It looks like something you'd use to knit a sweater, but don't let its appearance fool you. Run this exact thread through a gauntlet of extreme heat, toxic gas, and immense physical tension, and it transforms into the backbone of modern engineering. It becomes this, carbon fiber, 5 times stronger than steel, twice as stiff, and a fraction of the weight. You know the final product, but the process of making it is an absolute nightmare of chemical engineering. Today, we are going deep into the crucible. We're going to look at the molecular violence required to manufacture carbon fiber from its raw state, a polymer called Polyacrylonitrile, or PAN. Over 90% of the world's carbon fiber starts as PAN, but you can't just melt it into shape. If you heat PAN like normal plastic, it just burns. To make carbon fiber, we have to strip away everything that isn't carbon, without destroying the fiber itself. Here is exactly how that happens. Step 1 is making the precursor fiber. PAN is a synthetic resin, specifically a linear polymer. Its molecules look like long, tangled chains. To turn this raw powder into a thread, engineers use a process called wet spinning. The PAN is dissolved in a solvent to create a viscous dope. This syrup is pumped under high pressure through a spinneret directly into a chemical coagulation bath. The solvent washes away and the PAN solidifies. The PAN immediately solidifies into filaments. These are stretched out while wet to help align those polymer chains parallel to the fiber. At this point, it's white, it's relatively weak, and it's mostly just acrylic yarn. Now the torture begins. We have to lock its structure. If we put this white fiber straight into a 2000-degree furnace, it would instantly melt. Before carbonization, we must lock its structure in place. The fibers are fed through ovens running between 200 and 300 degrees Celsius. But here is the critical trick. The fiber is kept under immense physical tension. As the heat rises, the chemistry fundamentally changes. The heat causes the nitrile groups in the polymer to react and cross-link. This converts loose, linear spaghetti into a rigid, thermally stable ladder polymer. Oxygen bonds with the chains to stabilize them for the next stage. Because we keep the fiber pulled tight, these new molecular ladders are forced to align perfectly straight along the fiber's axis. This is where strength begins. By the time it leaves the oxidation oven, it is completely black. It is no longer a plastic. It is an infusible, fireproof structure. It is now ready for the void. Welcome to carbonization. The fiber enters a furnace operating at up to 3000 degrees Celsius. But there is a catch. 0 oxygen is allowed. If there was oxygen, the fiber would instantly combust into ash. Instead, the furnace is flooded with inert nitrogen or argon gas. This is where the magic happens. Without oxygen, the material cannot burn. Instead, the extreme thermal energy causes non-carbon atoms to literally shake themselves loose from the structure. Hydrogen and nitrogen atoms are expelled as exhaust gases, including highly lethal hydrogen cyanide. This makes industrial safety engineering just as complex as the furnace. As the non-carbons leave, the remaining carbon atoms bond tightly to each other, forming microscopic graphene ribbons. The hotter the furnace, the stiffer the fiber. When the fiber exits, it is pure carbon. It is incredibly strong, but there's a problem. It's too perfect. The surface is chemically inert, meaning nothing sticks. Carbon fiber is useless if it can't bond with epoxy resin. To fix this, it goes through an electrolytic bath, applying a controlled electrical current in a chemical soup. This slightly oxidizes the surface, creating microscopic roughness and active chemical hooks for the resin to grab onto. This is the glue trap that makes it a composite. Finally, it gets sized. A micro-thin layer of polymer is coated onto the fiber to protect it from breaking during shipping and weaving into parts. And there you have it. You take a spool of acrylic yarn, stretch it, bake it until the molecules lock, and blast it with thousands of degrees of heat. It is a process where chemistry and extreme mechanical engineering meet perfectly. The result is the backbone of modern aerospace and hypercars. If you want to see how we weave these threads into a finished Formula 1 chassis, hit subscribe and check out the next video. Thanks for watching.